So the bell work today is calculating an empirical formula. It says that NutraSweet, this sugar substitute, is 57.14% carbon, 6.16% hydrogen, and 9.52% nitrogen, and 27.18% oxygen. Calculate the empirical formula of NutraSweet. So anytime we see the word empirical formula, we're going to have to remember the poem that we learned yesterday. And that is percent to mass, mass to moles, divide by smallest, round till whole. So the first thing I'm going to need to do is take the percent and go percent to mass. And that's what I'm going to do here. So I'm going to start out with 57.14. And I'm going to assume 100 grams. And when I do that, I can go ahead and say that if I have 100 grams of this compound, 57.14% is going to mean that I have 57.14 grams of carbon. And I'm going to do the same for the others. So 6.16 grams of hydrogen, and I have 9.52 grams of nitrogen, and finally I have 27.18 grams of oxygen. So now that you have converted mass or percent to mass, you can convert grams to moles. So our poem goes percent to mass, mass to moles, divide by smallest, round till whole. So step 1 was percent to mass. Step 2 is mass to moles. So there are 12 grams of carbon in every 1 mole of carbon, and that is our molar mass calculation. There is 1 gram of hydrogen for every single mole of hydrogen. And there are 14 grams of nitrogen for every 1 mole of nitrogen. And there are 16 grams of oxygen for every 1 mole of oxygen. When I calculate carbon, I get an answer of 4.7616, and it's repeating. And so with sig figs, I'm going to go ahead and take 4 sig figs, 4.762, and that is moles of carbon. With hydrogen, I get, of course, 6.16, and that is moles of hydrogen. And then for nitrogen, I get a value of 0.68, and that is for moles of nitrogen. For oxygen, with sig figs, I get a value of 1.699. And that is moles of oxygen. Okay, percent to mass, mass to moles, divide by smallest, and round till whole. So I'm going to divide by the smallest, and in this case, the smallest is 0.68. So I'm going to go ahead and divide everything by 0.68. For carbon, I get a value of 7.00. For hydrogen, I get a value of 9.06. For nitrogen, it is going to be 1 exactly because I'm dividing by itself. And for oxygen, I get a value of 2.49. And the last part would be to round till whole. So percent to mass, mass to moles, divide by smallest, round till whole. So what I need to do now is round till whole. So this is going to round to 7. This will round to 9. This stays at 1. Now, right here, we are right in the middle of 2 and 3, right at 2.5. This is something that we have not learned quite yet, and what we're going to do is, that's why we did it for Bellwork, so that we could segue into this process here. So if you got stuck here, it's a good thing, because it's something that is kind of an exception to our rule so far. So when you get a number that is right between 2 and 3 in this case, what we have to do is scale up everything else. So this is so close to 2.5, it's hard to go to 2 and it's hard to go to 3. I don't really know which way to round it. And if I round to 3, then I'm cutting half short. And so I can't have a compound that is 7, 9, 1, and 2.5. So in this case, something that I have to do is actually scale up everything by a factor of 2. So in some cases, I'm going to get an answer that's right in between. In this case, I have to multiply everything by 2 to scale it up. So I'm going to have 14, 9 times 2, I'm going to have 18, and then for the nitrogen, I'm going to have 2 instead of 1, and then now the 2.5 after I multiply by 2 is going to be at a nice even whole number of 5. So our final formula, the final empirical formula, is going to be C14 H18 N2 and O5. So make a note to yourself, put it on your notes, put it in the mole packet, and be aware that when something is right in between, like this, like 2.5, we don't round to the nearest whole number in this case because it's so close to the middle. So in that case, we have to double everything else in order to make it a whole number. Okay. So up to this point, we've covered our mole diagram that converted representative particles to moles, and then grams to moles using molar mass, and then liters to moles using 22.4 molar volume. We have covered percent composition, and now we have covered empirical formulas. That's what we covered yesterday. And now we are going to cover molecular formulas. So that's what we're doing today. Today we're going to basically be scaling up the empirical formulas to find the correct molecular formula that we need in order to know exactly what the compounds constitute in this molecule. It may not be the empirical formula, it may be something more complex. So the molecular formulas are the true formulas, or the actual formulas. So these contain the same whole number ratio for the subscripts, but it may be scaled up. It might be some sort of multiple of the empirical formula. So all we have to do here is find that multiple. What number in this case, and it can be a whole number, 1, 2, 3, 4, 5, which whole number is going to be used to scale up the empirical formula, to scale up that ratio? Well, the formula to do that is here. So I recommend giving it a puffy cloud of greatness. N equals the GFM over the EFM. So what we have to do is take the gram formula mass of the compound, and we are going to have to divide it by the empirical formula mass. Once we find the multiple N, and it's going to be some sort of whole number, we're going to have to multiply each subscript by this N in order to get the formula. A white powder is analyzed and found to have an empirical formula of P2O5. The compound has a molar mass of 283.9 grams. What is the compound's molecular formula? So we are given the molar mass of the actual compound, and we have found the empirical formula. So this is what we did yesterday. We actually found this empirical formula. So what we're going to have to do is find the multiple. So here we go. I'm trying to find some whole number n so I can scale up my empirical formula. To do that, I'm going to take the GFM divided by the EFM. So the EFM was calculated for me, P2O5, 142 grams per mole. So if I'm plugging it in, n is going to equal, the GFM was given in the problem, 283.9. That is the mass of the actual compound. And the mass of the EFM was 142. Grams. When I divide this out, when I multiply this out, I get a value of 1.999, which is right at 2. So this number here is just at 2. So I am going to be using this whole number in order to scale up my empirical formula. So I'm going to take that 2 and multiply it by P2O5. So my true formula, or my molecular formula, is going to be P4O10. I have scaled up this formula to its true mass and its true formula. This is called the molecular formula. Okay, so here is the mother of all problems of this section. This is the longest one that we will do, and it's because it includes several different parts here. We're looking at percent compositions, we're determining empirical formulas, and then we're scaling it up to the molecular formula. So it's a lot of stuff in one. If you can understand this problem, you're doing really well. It says a compound is used as an additive for gasoline to help prevent engine knock, and it shows the following percent composition. 65% chlorine, 24.27% carbon, and 4.07% hydrogen. Determine the empirical formula. So right away I see empirical formula and I'm thinking of the poem. And determine the molecular formula for this compound. And then it gives me the molar mass of my actual compound here, which I'll use later after I determine the empirical formula. So, first things first, I have to determine the empirical formula. So, step 1, percent to mass. I assume 100 grams of this compound. So I'm taking 71.65 grams of chlorine. I'm taking 24.27 grams of carbon and 4.07 grams of hydrogen. Next thing would be to convert mass to moles. So percent to mass, mass to moles. So I have 35, this is from the periodic table, 0.5 grams of chlorine for every 1 mole of chlorine. For carbon, 12 grams of carbon for every 1 mole of carbon. And for hydrogen, these are always nice because hydrogen is just 1 gram per mole. For chlorine, I get, with 4 sig figs, 2.018, and that is moles of chlorine. For carbon, I get 2.023 moles of carbon. And for hydrogen, of course, it will be 4.07 moles of hydrogen. Percent to mass, mass to moles. Next thing to do would be divide by smallest. And in this case, my smallest value comes from chlorine, 2.018. 2.018. 2.018. For the first one, I get a number that is exactly 1. For carbon, I get 1.002. And for hydrogen, I get 2.02. Percent to mass, mass to moles, divide by smallest, and round till whole. So this stays at 1, this will round to 1, and this will round to 2. So my empirical formula, my EF, is going to be, so I have chlorine, and there is 1. There is carbon with 1, and then H2. So this is ClCH2. This is my empirical formula. So I'm given the molar mass of the compound. What I have to do is take the molar mass of my empirical formula so that I can solve for the molecular formula. So I'm going to add up. Chlorine is 35.5. Carbon is 12. And there are 2 hydrogens. So that is going to give me 2 grams. When I add this up, I will be getting 49.5. Whoops. 49.5 grams per mole for the empirical formula. So this is the molar mass of this empirical formula. Now I need to calculate the molecular formula, and to do that I need to use the equation N equals GFM over EFM. So I'm going to take the GFM, which was given in the problem, 98.96 grams, and I'm going to divide that by the EFM, which I just found, 49.5 grams. And the answer I get there is 1.999. So I round this up to the nearest whole number because that's what I'm going to be scaling up my compounds by. So I'm going to take that 2 and multiply it by my empirical formula, ClCH2. And my final compound is going to be Cl2, C2, H4. This is my true formula, or what we call the molecular formula. So, if you can do the empirical formula, remember your poem, and then you can include it into a molecular formula or molecular problem, then you're doing really well. So this is kind of it all together in one single problem.